Hello grade 11s, my name is Claire. Welcome to Learn Extra. In this session we're going to be looking at linear programming. Linear programming is a section of mathematics where we deal with constraints and feasible regions. In this session we're going to focus on linear programming problems and strategies, and we're going to have to translate words into constraints, and then we're going to have a look at translating a feasible region into constraints. Now, constraints is just a really fancy word for a system of inequalities. What a linear programming problem involves is that the first thing we need to do is we need to work out what these constraints are in terms of x and y. The second thing that we need to do is we need to have a look at sketching our feasible region. That means that we have to shade in where all the inequalities overlap. The third one is we're going to have a look at our objective function. Now, often this involves us having to look at profits, and obviously we want to maximize profits, so we look at where profits are a maximum. Or we're going to have a look at where costs are a minimum. So we're always looking at a biggest or a smallest. In grade 11, we have to do this using the vertices method. When you get to grade 12, we'll do it in a different manner using the search line. But you can do it using either the vertices or the search line when you get to an exam. And then once we've done this, we will physically work out the minimum costs or the maximum profits, or those values that we are optimizing. So let's get straight into it, and we are going to have a look at translating the words that we're given into constraints. Now, often it's a bit of a problem because it's words and mathematics. So what we're going to do here is we're going to take it slowly and have a look at the different words and what they mean to us. So the first one, the sum of x and y. Well, first of all, before we read any further, sum to us isn't just a problem. Sum should mean for us plus. So out of that, we need to be able to add x and y together. Then, if we have a look, we are adding x and y. But now, it says to us the sum has a minimum value of 2. Now, when we're setting up constraints, constraints are based on inequalities. Inequalities are the symbol that goes like that. Or, if I wanted to, it would be the other way around. But we need to work out which one we need. It says we need a minimum value of 2. So the best way that we can do this is to look and say, all right, we've got a number 2. There's our number 2. Which is the smallest? The sum of x and y or 2? And in this case, 2 is our minimum. So that means that our inequality has to face everything that's not the minimum. In other words, it's going to face the x plus y. The other thing is that I put the equal sign in with the 2 because a minimum value is actually 2. I'm allowed to have 2 if I say to you it must be a minimum of 2. That is the smallest value I'm allowed to have. Other than that, it's got to be bigger than 2. So it's got to be a number like 3, 4, 5, etc. So here we're going to have the sum, which is bigger than 2. That's a different way of saying the sum of x and y has a minimum value of 2. Okay, let's have a look at the second part of that sentence. The second part of that sentence says the sum of x and y has a maximum value of 8. So again, sum for us should mean plus. Plus, I take the x plus the y, and I've got 8 as a reference point. Now with the inequalities, I need to work out, well, which one should my inequality face? Remember, my inequality opens to the biggest number. So here, my biggest number is going to be 8. So I would take my inequality and face it open towards the 8. That means that the sum of x and y is smaller than 8. So 8 is my maximum value. Again, notice I've put the equals to sign in. The equals to sign means that I'm allowed to have 8 as a value. Well, if I'm looking at a maximum value of 8, the most I'm allowed to have is 8. So I can equals 8, which is why we put that in. Okay, so that's separating it into two different inequalities. What I'm allowed to do as well is, instead of writing it as two separate inequalities, sometimes you might see this joined to have one line with two inequalities in it. Now look at what I've written there. I've written 2 is less than or equal to x plus y, which is less than or equal to 8. In other words, the sum of x and y, remember sum says plus, so we've taken x plus y, and that has to have a minimum boundary of 2. Smallest is 2, biggest is 8. So my inequalities will always face towards the biggest sign. So they face that way, and I've got 2 on this side, left-hand side, the smallest side, 8 on the biggest side. If you write down both of the ones on the left-hand side, or just the one on the right-hand side, they mean exactly the same thing. So two different ways of writing down the same sentence in mathematics. So that's the first type of constraint that we get. Let's go to the second constraint. The second constraint says, at least 2 of x and at most 3 of y. Oh boy. Well, what happens here is we must separate it into two parts. Let's deal with the x first, because it doesn't give me a relationship of x and y together. It gives me a relationship with just x and then just y. So the first thing I do is I say, okay, x has a relationship with 2. So we write down x and 2. The relationship is there must be at least 2 of x. So again, we've got to work out, well, one of them has got to be smaller, one of them's got to be bigger. If I have a look at that, at least 2. In other words, 2 has to be the smallest amount. And if 2's got to be the smallest amount, then my inequality has to open towards the x. Again, if I'm allowed to have 2, then I can put the equals to sign. And it didn't say more than 2, it said at least 2. So in other words, 2 is the bare minimum I'm allowed to have. Okay, that's fine. What about the next part of the sentence? Remember, the second part of the sentence is dealing with y, and y has got nothing to do with x in this situation. So if I have a look here, I'm going to take y and 3. And y, there must be at most 3 of y. Again, it's an inequality. All of these constraints work out to be inequalities. So I need to work out which is the smallest, which is the biggest. So I've got 3, at most 3. So in other words, 3 is my ceiling. I can't go beyond 3. So my inequality has to open towards 3. Also, I can have at most 3. Can't go beyond it, but I can have 3, which means that my equals to sign has to be there. Okay, what's eventually going to happen is these are going to translate into graphs. So at the back of our minds all the time, we must be thinking, what type of graph am I ending up with? So if we quickly go back to A, x plus y is less than or equal to 8. Bit difficult because of the inequality sign there, But if I took out that inequality sign and I had x plus y is equal to 8, we would be able to work out what kind of graph we've got. And in this case, the kind of graph that we've got is a linear graph. But it's a linear graph that has got a gradient. So we will later on see that we're either going to end up with a graph. Remember, a linear graph has a negative gradient when it looks like that, and a positive gradient when it looks like that. So our graphs are going to be based on the linear function. Similarly, if I have a look at x and the 2, x is greater than or equal to 2, x equals 2 is a straight line, and we need to not forget that. But remember, it's a very special kind of straight line. It's a straight line that's got no gradient. So a line that has got no gradient is one that's perpendicular to the x-axis. In other words, it is vertical. The y is less than or equal to 3 is going to translate into a straight line. Again, kind of a special kind of straight line because it has a gradient, very specifically, equal to 0. And that for us translates into a horizontal straight line. We should be familiar with these kinds of lines when it coming from the hyperbola. So we shouldn't have too much of a problem with them, but just to remind you that they are actually straight line functions, and we will shade them a bit later on. Okay, let's have a look at the next kind of inequality. The next kind of inequality often gives us quite a few problems because it has that horrible thing called a ratio in it. So it says the ratio of y to x. It's very important for us to remember that a ratio can be written in two different ways. It can be written as y is to x, like that. But again, that's confusing for us because what we want is we want it in a mathematical statement with the mathematical functions that we can work with. So that can be translated into a fraction. And it's probably easier for you to work with the fraction rather than the ratio. But we'll work with both anyway, just for the completeness sake. It says the ratio of y to x must not be smaller than 3 is to 5. So we've got y is to x and we've got 3 is to 5. So it's a very good idea to put them down separately like that. Okay? And it says the ratio must not be smaller than. So again, when we look at the constraints, we've got to work out our inequality, which is often the hardest part of this. So let's look. Must not be smaller than 3 is to 5. So if I'm looking at that, 3 is to 5 is going to be the very bare minimum I'm allowed to have. So everything else has to be bigger than it. And if it's got to be bigger than it, my inequality has to open towards what's bigger. So in other words, my inequality has to face that way. As with the previous examples, if it is not smaller than, I'm allowed to have a ratio of 3 is to 5. Just can't go smaller than that. I'm allowed to have the ratio of 3 is to 5, which means I'm allowed to put that equals to sign in. Okay, so how are we going to translate that into the fraction? Very simple, actually. The first number of the ratio becomes the numerator. The second number involved in the ratio becomes the denominator of my fraction. And again, we look at it and say, the ratio must not be smaller than. So my inequality opens to what's biggest, and the biggest is the y over x, not the 3 over 5. Okay, now that is really yucky for us to try and draw. Don't know about you, but it's been a very long time since I drew graphs of y over x. We are used to drawing graphs that have y equals to something. So let's have a look and see. Linear programming example generally works with x and y values that are positive. So we're looking at, for argument's sake, the number of rooms. We can't have a negative number of rooms in a house. Or we're looking at the number of liters of oil. It would be really silly to have a negative number of liters of oil. In fact, we can't. So all these things that we're dealing with are positive values. So if I work with the fraction here, we need to work out an LCD. And if we work out an LCD, our LCD, which stands for lowest common denominator, is 5x. But fortunately for us, the x is positive. So 5 times a positive number is still a positive number. So when I multiply the inequality by a positive, it doesn't cause any problems for us. Because remember, if it was negative, my inequality sign would have to change around. So we're quite lucky here. In all linear programming examples, we will only deal with positive x and positive y's. So in this case, I can then translate that inequality to something I understand a bit better. And I understand it a bit better if I multiply y over x by 5x. The x's simplify to being 1, because x divided by x is 1, and 5 times y is 5y. That is bigger than or equal to, the 5's cancel out with one another, 3 times x. Now that's a little bit easier for us to deal with. The other way to have a look at it, if you're more used to it, is to cross multiply. And again, we can cross multiply in this situation because our denominator is positive. So we're ending up with something that we can translate into a linear function. Okay. Example D. At least 2 of x to 1 of y. This is different to example B because here the x's and y's are related to one another. So it's very important that we put it into context. So let's have a look at probably the easiest way to do this is to say we've got an x and we've got a y. Remember, a ratio can be written as a fraction or it can be written in the format x to y. Okay, I prefer the x over y because we are more used to dealing with fractions. All right, then it says at least 2 of x. So where do I put that 2? Do I put the 2 in the numerator or do I put the 2 in the denominator? Well, it depends exactly where the x is. The 2 relates to x, so it must be in the same position that x is. So here, it's got to be in the numerator. 1 of y means that the 1 has got to be in the position where the y is. So here, we're going to put it in the denominator. If I'm doing it with the other ratio, the 2 needs to be in the same position as the x, and the 1 needs to be in the same position as the y. Okay, so now we're going to have a look at it. This inequality becomes a bit of a nightmare for us, but we're going to get it right. At least 2 of x to 1 of y. All right, so we want at least. That means that my ratio of 2 is to 1 is the smallest possible value. So if it's the smallest possible value, my inequality has to open to x over y. Similarly, with the ratio, it has to open to the x's to y ratio. Again, it can be equal to, because at least means that it can be in a ratio 2 is to 1. It can equal that ratio. It just can't be below it. So hopefully now we can translate that into something that we prefer to deal with. Remember, this is all about how we prefer to deal with it, rather than looking at something that we don't necessarily have a lot of experience with. So here we're going to say, I need to work out my LCD. My LCD is going to be 1y, which is y. So if I multiply by the LCD, or as some of you refer to it as cross multiply, I'm allowed to do that because my y is positive. That won't change the inequality sign, and I will end up with something that I can use. So if I multiply the left-hand side by y, I'm left with x. And if I multiply the right-hand side by y, 2 over 1 is 2. So 2 times y is 2y. As you can see, that now is in a format that we are more familiar with dealing with. Okay. Let's have a look at example E. Example E can be written or dealt with in 2 different ways. So I'm going to show you the 2 different ways, and then we can see which you prefer to deal with. So it says x may not exceed more than 3 times that of y. If I'm going to write that out as a mathematical statement, I've got x, which may not exceed, that's going to be an inequality, which we will talk about now, 3 times that of y. All right, quickly, let's pause. Times in mathematics would mean the physical operation of multiply. So if I'm going to say 3 times y, I can write it as 3y. Okay, so it says x may not exceed more than. So in other words, what do we understand by that? Is x smaller than 3y, or is x bigger than 3y? And sometimes the English does confuse us. Exceed means go bigger. So if it's not allowed to go bigger, then we have to be smaller. So in other words, out of that, what we have worked out is that the 3y is the biggest part of that statement. And if it's the biggest part of that statement, my inequality has to face the 3y. Okay, can I put an equals to sign there? Well, you've seen that I have. Why did I put an equals sign there? It says it can't be more than 3 times y. So can it be 3 times y? I think it can. Absolutely it can. If it's 3 times y, it's not bigger. It is 3 times y. So I'm allowed to have my inequality there and the equals sign there. Okay, I told you I was going to give you a second way to do this. Let's have a look at it in the ratio format. I don't necessarily like this particular example in ratio format because I think the sentence speaks for itself. We work from left to right with a sentence. We can come up with the answer quite quickly and easily. But I'm going to show you the ratio anyway. So the ratio format says to us that we've got x is to y, all right? X cannot be more than 3 times y. So in other words, we've got x as a ratio to y, and the x can't be more than 3 times the y. So in other words, 3 parts of x to the 1 part of y. And again, here our inequality is the ratio, the 3:1, is the biggest number. So let's translate that into a fraction. If we translate it into a fraction, we've got x over y and 3 over 1. Remember, 3 times that, remember that the 3 times goes to the x because it can be 3 times bigger than y. So here our inequality faces the 3 over 1, and I end up with the cross multiplication because I've used an LCD of y. Remember, my denominator is positive, so it doesn't affect my inequality. I'm allowed to multiply through by it, and if I do that, I get x is less than or equal to 3y, which is exactly the same as what we got by reading the sentence from left to right. Okay, let's try another one. It says y must be at most half that of x. Again, I can work with it as a ratio, but I think we're getting the gist of reading these things from left to right. So let's try and just do it from left to right. It says y must be at most, we'll deal with the at most now, half that of x. All right? Of, in mathematics, is what mathematical operation? It's times, that's right. Multiply. So a half of x is a half times x. All right, I said you would get back to the at most. The at most, does it apply to the half of x or does it apply to the y? It's very important for us to get it right because this affects our shading when it comes to the feasible region. At most means that it's the biggest, right? So the inequality has to open towards the half x because that's the biggest. All right, how are we doing? Cool. All right, let's now have a look at translating a feasible region that we've already been given into constraints. We've looked at going from words to constraints, but what if I give you a feasible region? How are you going to put that back into constraints? All right, one thing that we need to remember, and I'm not sure that we all know this, so I'm going to teach it to you quickly. We can work out the equation of a linear function by just knowing what its x and y intercepts are. All right, you're thinking we can do y equals mx plus c, get your gradient, get your y-intercept, and we can put it together. Absolutely, we can do that. But there's another way to do it. So let me show you that other way. If the intercepts are a0 and 0b respectively, there we go, a0 and 0b respectively, there are intercepts. What I can do is I can work out my equation of this straight line in the following format. It goes y over b is equal to x over a, plus x over a is equal to 1. I'll repeat that. Y over b plus x over a is equal to 1. Quite a sneaky trick, all right? So here, if we look at it, if my y-intercept was 0, 6, and my x-intercept was 4, 0, I could work out the equation of that straight line very easily by doing the following. I take y over the y value of the y-intercept, which is 6, plus x over the x value of the x-intercept, which is 4, and I make that equal to 1. Okay, we don't necessarily like the straight line in that format, but it is a format. So what I would do now is I would take an LCD. What's the LCD of 6 and 4? It is 12. You've got it. It's 12. So what I would do is I would take 12 and multiply it by y over 6. Well, the 12 is going to divide by the 6 and leave 2. So I'm left with 2y. If I take x over 4 and times that by 12, 12 divided by 4, you've got it. It's 3x. And the 1, well, what's 1 times 12? Quite simple for us, 12. Now that is an equation of a straight line. Some of you are going, no, we don't like it in that format. Well, if you wanted to change the format, we can do so quite easily. Let's go a little bit further to change that format, and let's go like this. 2y is equal to minus 3x plus 12. Again, 2y we're not so comfortable with, and if I change that, I get y is equal to minus 3 over 2x plus 6. Now you should be breathing a sigh of relief going, oh, that's okay. That's exactly what we wanted. So can you see from just having the x-intercept and the y-intercept, I can work out the equation of the straight line. But some of you are saying, hold on, there's shading. How do I get that shading involved? Okay, let me teach that to you quickly. If we have a look, our shading for this line is where? Is it above the line or is it below the line? When we look at shading, we always have to look at, is it above the line or is it below the line? And in this instance, okay, so with this straight line, we need to look at where our shading is. Is it above or is it below? And if you look here, I've colored below the line. In other words, that means that my inequality has to face away from the y. Okay, so how am I going to translate that into all this working? Well, for a constraint, my equal sign is going to change to an inequality sign, and that's where we need to pick it up. So here, my inequality sign for these, the y is the inequality must face away from the y. So here, the inequality must face away from the y, so it opens to everything that's not the y. So in this instance, I would replace the equals to sign with a less than or equals to inequality. And that would just translate the whole way down. So instead of the equals to 12, it would be less than or equals to. Have I broken any inequality rules by multiplying through by a positive LCD of 12? I don't think so. Remember, if I multiply by a positive, my inequality stays the same. The only time alarm bells should be ringing is if I multiply by a negative. But that's not going to happen in linear programming because we always deal with positive numbers in linear programming. So we don't actually need to worry about my inequality. So if we carry on, we would have the inequality sign facing the minus 3x plus 12, and similarly it would face the minus 3 over 2x plus 6. So from that, we have ended up with an inequality given the graph. Okay, I've got 3 other lines there. Let's have a look at those lines. Remember I said to you a little bit earlier that we've got 2 special kinds of lines. The first line is a vertical line. Remember a vertical straight line? A vertical straight line doesn't have a gradient. So we have a small problem when we come to putting it together because we don't have a y and an mx plus c. So what do we have? Well, a vertical line, remember the asymptotes from a hyperbola, a vertical line is in the format x is equal to. Okay, so what's the number here? What's the number for this vertical line? Well, if we have a look, in this instance, it's E. I've been given that point all the way down at the bottom. So here I would put X and E together. Now E would generally be any particular number. In this case, if we had a look, we could make up a number, probably 2 or 3 or something like that, but let's just work with the variable for now. So we also need to look at our shading. Remember, shading is either above or below. But hold on, we now have a problem because we have a vertical line. So above actually doesn't work for us. So what we need to have a look at is the right or the left of the line. If it's the right of the line, I'm working with bigger numbers. So everything to the right of that number is bigger than. Everything to the left is smaller than. So here, my shading is to the right. So which one's bigger, X or E? In this case, E is bigger. So I would have my inequality facing E. Some of you are saying, but why am I putting the equals to sign there? Well, for a very simple reason. I have been given a solid line in the graph, and that solid line translates to the equals in the inequality. So for the one we did previously, there has to be an equals because that line is solid. It's very rare that you will get a non-solid line. So we don't generally do questions like that. If that was the case, the graph would be dotted. But seeing as though most questions don't involve the not equals to, we just deal with the equals to. Okay, so we've dealt with 2 of the lines here. What about the third line? Okay, we're going to have a look at the flat line here. Okay, flat line is a horizontal line like that. Remember, I said to you a little bit earlier that this is a very special line. It is a straight line that has no gradient. So if it has no gradient, I can put it into the format y equals no x's plus c. So it is literally just a case of y and a number. So here, if we have a look at that, this is going to be y and a number. But where do I read that number off from? Okay, I've given you various points on this picture. Remember, you cannot forget your graph knowledge when it comes to linear programming. Because we're still working on a Cartesian plane, we just chosen, or we have to work in quadrant 1 because of the positiveness of our x and y. So here, you've been given a point C, D. Which one relates to the y? Is it the C or is it the D? Hopefully we can remember our functions knowledge and our Cartesian plane knowledge and know that the D relates to y. Again here, we've got to put an inequality in because the inequality has come from the shading. So, again, I said to you earlier, above means bigger, below means less than. So, is D bigger than y or smaller than y? And if it's above, what we're doing is we are shading everything that is y. All right? If it's above, my inequality opens towards the y. So here, I'm saying to you that D's the smallest y value that I can have. And that's how it translates. And the last line that's here, is this one. Now this is a very funny line for us when it comes to linear programming because most of our linear programming examples translate to negative gradients. So in other words, we have ones like this. But here, I've given you one that's a positive gradient. So what I need to do is you need to realize that a positive gradient line in linear programming comes from a ratio example. And a ratio example ends up having y on the one side of the inequality and x on the other side of the inequality. So here, I'm going to have y equals mx plus c. So what I need to do is I need to work out the gradient. So let's not write the x there quickly. Let's just work out the gradient. The gradient means I need 2 points. Okay, let's go look at our graph. Here's a point, CD, and where's the other point? Hopefully, you've realized it is the origin. That gives us 2 pieces of information. The first piece of information is that the y value of the y-intercept is 0. So in the straight line, y equals mx plus c, that c value is 0, which helps us a lot. The second thing the line does for us is it gives us a second point. It gives us the point 0, 0. Now, that for us gives us 2 pieces of information. The first piece of information it gives us is that the y value of the y-intercept is 0. All right, so if I have y equals mx plus c, I'm going to end up with y equals mx plus 0, which is a great help in working out the equation of the straight line. The second piece of information it gives us is a point that we can use in reference to find our gradient. So here we have 2 points. So an option to work out the gradient is to work out the rise over run. The rise, we go from 0 to d. So from 0 to d is plus d. So it would be d over the run, which is c. So here we're going to end up with d over c and x. All right? But some of you might not like that, so we could use the gradient formula, which is the change in y over the change in x, and you're going to end up with exactly the same answer. But again, this is a constraint which involves an inequality. So we need to look at where the shading lies. Does it lie above the line or does it lie below the line? So here, if I shade it, I've shaded above the line. So in my inequality, does that mean my inequality sign opens towards the y, or does it mean it faces away from the y? Well, if it's above, it opens towards the y. So here, my inequality would be y is greater than or equal to d over c x. Again, it's an equals to sign because it's a solid line. Okay, let's move on and have a look at how we can put all of this together. So we're going to have a look at some example questions. Question 1. We're going to consider the following constraints. The sum of x and y is at least 10. Can all of you get x plus y is greater than or equal to 10? Let's quickly see if we can do that again. Sum means plus. So x plus y is at least 10. 10 is the smallest piece. So x plus y has to be bigger than. So my inequality has to face that part of the equation. Second equation, x must be at most twice that of y. Remember, this one we could do in 2 ways. I prefer to read it from left to right. So x must be at most twice that of y. At most means that the inequality faces the biggest thing, and the biggest thing in this instance is 2y. The third inequality, y must not exceed 8. In other words, 8's the biggest number. Remember that word exceed? Exceed means go beyond. If it's not allowed to go beyond, we stop at 8. Okay, those constraints are luckily enough given to us. Sometimes we're going to have to work those out ourselves, and hopefully now you're able to do that quite confidently. Let's have a look at the next part of any linear programming question. And any linear programming question now says, sketch the constraints and the feasible region. All right, that means we've got to take those 3 inequalities and make a picture out of it. We've got to use the space below to show our working. Most times in an exam paper, you will be given the grid. If you're not, you're going to have to draw it. Just remember to be sensible about your scale. But luckily enough for us in this one, we've got the grid. So we've got x plus y is greater than or equal to 10. That must be a straight line. But what kind of straight line is it? It has to be a horizontal one, a vertical one, one that's got a positive gradient, or one that's got a negative gradient. Okay, let's have a look at a very quick and easy method for us to work this out. X plus y is greater than or equal to 10. Remember, for us to draw a straight line, how many points do we need? We need 2 points. Very nicely for us, we could get the one on the y-axis, commonly called the y-intercept, and we could get the one on the x-axis, called the x-intercept. That means we could take those 2 points together and join the dots. But what do we know about a y-intercept? Well, a y-intercept doesn't change from graph to graph. A y-intercept has x equal to 0. So here is my inequality. And I want to work out the y-intercept. So the y-intercept means that x is equal to 0. So the point is going to be 0. And now I sub in to work out the y value. So if I sub in, basically you can cover the x because x is 0. And even if there was a coefficient there, anything times 0 is still 0. So we can cover it. Now, if we solve y and 10, remember, when we're working with this, we're working with the straight line. So we're treating that inequality as if it were an equals to sign. So here, we've got y is equal to 10. Easy for us. We now have the y-intercept. Similarly, we can work out the x-intercept. What is special about an x-intercept? In any graph, an x-intercept has one property we know about. It is that the y value is 0. So, if the y value is 0, I can also do my cover-up method. There we go, y is gone. So, I treat the inequality as an equals to sign, and I've got x equals 10. Bonus! Now I can join the two dots. So I would take my 0, 10 and plot it, and I would take 10, 0 and plot it. And now I would join the two dots. So here, 10 to 10. Remember to join the two dots with a straight line. It is a straight line after all, so use your ruler. All right, let's have a look at the other ones. Hopefully we're happy with that. Let's have a look at the other ones. X is less than or equal to 2y. Remember, when we are sketching this, we will sketch the shading afterwards. We're first worried about the straight line. So we need to look at the straight line x equals 2y. All right, I don't know about you, but I would prefer to get that into y is equal to. So I can divide by 2. And I end up with a half x is less than or equal to y. That makes it a little bit easier for me because I know how to draw the straight line y equals a half x. First of all, I work out its x-intercept and its y-intercept. But in this instance, we hit a snag because if I take x equals 0 and substitute, what do I get? A half times 0 equals 0. Oh dear, I've ended up with the point 0, 0. Not too much of a problem though, because there it is, 0, 0. But that's the x and the y-intercept. So we do have to work out one more point. So you can choose. Choice is a wonderful thing. We can choose an x value to substitute so that we can work out the corresponding y value. I am going to choose to take x equals 4. So if x equals 4, then I end up with a half times 4, and what do I get as an answer? I get 2. So the point that needs to be plotted is 4, 2. Okay, let's go plot the point. Well, 4 is our x and 2 is our y. So it's going to be over there. Now I've got 2 points. Now I can draw the straight line that joins them. So here we go. There we go. And it goes through it. All right. Remember, I extend that straight line. I'm not just going to draw it between those 2 points because it's an extended line. Technically, I should actually have an arrow on the end there. But for the purpose of the question, we don't need to go towards infinity. We can just have it like that. All right, there was one more inequality. The other inequality is y is less than or equal to 8. So you need to be asking yourself, what kind of straight line is y is less than or equal to 8? What kind of straight line is y equals 8? Let's think. We've got 4 types of straight lines: horizontal, vertical, positive gradient, negative gradient. It's a horizontal one. What's special about it? It's a horizontal line that passes through y equals 8. So here we go. I'm going to plot y equals 8, and I'm going to draw a horizontal line. That means that I take my ruler and I draw the line parallel to the x-axis. All right, that's drawing the straight lines, but I haven't taken into account the inequalities. It's easier to take into the account the inequalities once the lines are drawn. So how do we do this? Okay, we are going to say x plus y is greater than or equal to 10. So remember, if we're going to shade, shading has to be above the line or below the line. How do I know? Well, if the inequality faces the y, then it's got to be above the line. So here's the x plus y equals 10 line. I'm going to shade above. So that means anything this side of the line is viable. Is it? Well, not really, because I have 2 other constraints to take into account. Now you will see that I actually needed to extend my lines quite a bit. All right? And I'll show you why I needed to extend my lines. And we'll go back and extend them. It's not a problem if you hit this snag. So here, the shading's got to be this side. Let's have a look at x is less than or equal to 2y. Again, I look at where the inequality is facing. If it is facing towards the y, I shade above the line. So this was the line y is equal to a half x. So I'm going to shade above that line. And if I shade above that line, I'm shading here. But I need to take into account where the overlap happens. So technically, I didn't need this, because that's not where any overlap is going to happen, because I've already excluded this part of my graph. Let's have a look at the y and the 8. Where is the inequality facing? It's facing towards the 8, away from the y. So here we shade below. Now look here, this is why I said to you I would probably have to extend my lines, because at this point in time, my feasible region is open-ended. Not too much of a problem. Let's go back and extend the lines. I can extend that line all the way over here. Okay? And this one I can extend all the way, whoopsie, I want to extend it. So I'm going to delete it, and then we're going to draw it in again. There we go. And if you have a look, they actually do meet. They actually do meet. So my feasible region is the enclosed part. Now obviously I've written over there, you wouldn't, you would have your working somewhere else, but the feasible region is the enclosed part. And it's important for you to shade it. Some people prefer to shade everything that's not the feasible region, but it's more normal to shade the bits that are the feasible region. Okay, that is how we do that one. Now, let's go on and see what's the whole purpose of this. Well, the whole purpose of this is to maximize or minimize. That's why we do linear programming. We're looking for an optimal situation. What makes the constraints optimal? So here, we're going to maximize or minimize the following expressions. Now, most times in any test paper, you will be given one option. You won't have to maximize and minimize. This here is just to show you what to do. And again, in grade 11, we do it using the vertices method, and in grade 12, we do it using the search line method. So next year, you will have a choice whether to work with the search line or the vertices. But for grade 11, we work with the vertices method. What does that mean? All right, let's have a look. We're going to maximize or minimize the following expressions. So we go to our graph. We go to our graph here, and we're going to maximize the expressions. The first expression, let me take all of this stuff away so that we can see what we're doing here. So we're going to take all of this away, and we're just going to be left with the feasible region. My feasible region is here, and I want to maximize P is equal to 5x plus 7. That's what your notes say. So P is equal to 5x plus 7y, sorry. All right, so we need to have a look at the vertices method. The vertices method says I must find out all the vertices of my feasible region. That means I've got to look here at that point. Let's call it A. Give it a name. This point over here, let's call it B. And this point over here, let's call that one C. Now, on an accurate graph, you can read these things off. So the first point here, if I read it off, it's going to be 2, 8. 2 for the X, 8 for the Y. So A is 2, 8. B, if I read it off, well, the B also has a Y value of 8, but my scale doesn't go up to that, okay? What if I do want to work it out? Okay, well, here, this is the line Y is equal to a half X. So what I would do is I would equate Y is equal to a half X to this line Y is equal to 8 and solve them simultaneously. If I do that, I get 8 is equal to a half X, so 16 is equal to X. So the X value at B is 16. Most times you can read off that point. So don't have too much of a panic to work out that as a simultaneous equation. And see if I wanted to have a look at what that is. I'm also going to read it off, or we can solve simultaneously. If I read it off, it's a bit difficult here because I don't have a grid, but the answer is 6 2/3, 3 1/3. Let me show you how we got that algebraically for those of you who are quite keen to do the algebra. Here it is. The line is y equals to a half x, and x plus y is equal to 10. Those are the lines that C lies on. So I'm going to take those two equations and solve them simultaneously. So I take x, instead of y, I'm going to write what it's equal to. And it's equal to a half x. So now what happens is I get 1x plus a half x, which is 1.5x, equals to 10. And I'm going to multiply by the LCD of 2. So I get 3x is equal to 20. And now I'm going to divide by 3. And I get 20 over 3. If we use our calculators, we will see that 20 over 3 is 6 2/3. Once we've got that, we can go and work out what the y is. That means take the x equals to 20 over 3 and substitute it into y is equal to a half times 20 over 3, a half x, which is 10 over 3. Is it a problem that I used the half x? No. Could I have used the x plus y equals 10? Absolutely. You will see that 6 2/3 plus 3 1/3 is 10, which means it satisfies that line. So we have our vertices, which is great. So here, if we have a look, our vertices are A, that was 2, 8. The second vertex was B, 16, 8. And the third vertex was C, 6 2/3, 3 1/3. Now, I need to see which of those points maximizes or minimizes this expression. So I'm going to do 3 calculations. The first calculation is P is equal to 5 times 2. I substituted. I took x equals to 2 and substituted it in. Then I'm going to take plus 7 times the y value, that is 8. 5 times 2 is 10. 7 times 8 is 56. 10 plus 56 is going to give me 66. So in order to get the optimal function there, the value that comes out at the point 28 is 66. I have to go and redo that calculation with the point 16.8. So here, P, 5 times 16 plus 7 times 8. Now 5 times 16 is 80. That's okay, we can use our calculators or we can use our heads. 80 plus 56 is 136. Now let's have a look at the next one. The next one you might want to use your calculator for, but it's okay if we don't. All right? The next one I'm going to take P and 5 times 6 2/3 plus 7 times 3 1/3. I would literally enter that into my calculator, and if you do that, you will get an answer of 56.7, or actually 56 2/3. All right, so let's be proper about it and put 56 2/3. Now let's answer the question. The question says to us, we want to maximize and we want to minimize this expression. So, which is the biggest number out of 66, 136, and 56 2/3? You got it. 136 is the biggest number. So, we are going to maximize. It is maximum at 16.8. So in other words, the coordinates, the point that maximizes that expression of P equals 5x plus 7y is 16.8. But what if the question says to me, What is the maximum value? Well, we've worked it out. The maximum value is 136. Okay, but we were asked to do two things. We were asked to maximize and to minimize. So just as for the maximum we took the biggest, the minimum we have to take the smallest. So here, which is the smaller number? 66, 136, 56 2/3. You've got it. It's 56 2/3. So our minimum is here at which point gave us 56 2/3? Oh, it was the point 6 2/3, and its y value was 1 1/3. Again, if I said to you, grade 11s, what is the minimum value? You would have to tell me the minimum value is 56 2/3. Have we got it? Let's try one more example on this and see if we've really got it. Okay, we need to maximize and minimize p equals 3x plus 3y. All right, we've already worked out the points of intersection, so I'm not going to go and repeat that. What I will do is I will just write them down again. The points of intersection were A, 2, 8, B, 16, 8, and C, 6 2/3, 3 1/3. Those were our points that were at the end of our feasible region. So again, what method must I go to figure out which is the maximum, which is the minimum? Which point gives me the maximum, which point gives me the minimum? You've got it. We substitute. So here I take P and I take 3 times 2 plus 3 times 8. 3 times 2 is 6. 3 times 8 is 24. If I add those together, I get 30. Next one. P is equal to 3 times 16 plus 3 times 8. 3 times 16 is 48. 3 times 8 is 24. So if I add those two together, I get 72. Next one, P is equal to 3 times 6 2/3 plus 3 times 3 1/3. 3 times 6 2/3 is 20. 3 times 3 1/3 is 10. So if I add those together, I get 30. Now, grade 11, what is the maximum and the minimum value of my expression for P? The maximum is very easy to figure out. The maximum is 72, isn't it? So we're going to put here that this is a maximum at 16.8. And again, what is its maximum value? I've worked it out already. Its maximum value is 72. Now I'm going to ask you, what's the minimum value? Some of you are going, but there are 2 minimum values. That's okay. We're allowed to have 2 minimum values. In fact, sometimes there are more points than 2 that give us our minimum value. So here, 30 is our minimum value. And if you have a look at our feasible region, I'm going to take you back there quickly. If you have a look at our feasible region, all points along this line here will actually give me a minimum value. But according to the vertices method, we have got a minimum at x equals 2, y equals 8, and a minimum at x equals 6 2/3 and 3 1/3. So here, to answer the question, we would say that it's minimum at 2, 8, and 3 1/3. at 6 2/3, 3 1/3, because it's actually minimum at both of them, legitimately. And again, if I asked you for what is the minimum value, you're going to have to tell me it's 30. Well done. Okay, so let's have a look now and see if we can do a problem from start to finish. Question 2 says, during the preparations for the 2000 Olympic Games, MDP architects were given the task of drawing up plans to build a series of small hotels. In each hotel, there was to be at least one single and one double bedroom. In one of the hotels, the contractors found that the builders could build at least 7 bedrooms altogether, but not more than 12. The number of double bedrooms was to be at least twice the number of single bedrooms. The rate for a single bedroom is 300 Rand per night, and that of a double bedroom is 500 Rand per night. So, question 1 says, write down the constraints and hence use the graph paper to draw the feasible region. Okay, well, before we do that, in order to get a constraint, we need an X and we need a Y. So it's important for us to know what is X, what is Y. In most exam questions, they will say to you, let this be X, let that be Y. It just helps you to start. So what we're going to do here is we're going to let the number of single rooms be X, and we're going to let the number of double rooms be Y. So I'm going to put my constraints over here. And the first thing I need to do is I need to write that down. So we're going to say let the number of single rooms be X, and let the number of double rooms be Y. Okay, now let's go and translate the sentences into mathematical statements. So, the first sentence says to us, in each hotel, there must be at least one single and one double bedroom. What that means for us is that one single room, one double room. So the X and the Y, it was an at least. Remember, the at least is the smallest. So here my inequality faces the biggest number. And in this case, it's the X or the Y. So those are our first two constraints. The next sentence says, in one of the hotels, the contractors found that the builders could build at least 7 bedrooms altogether, but not more than 12. So we have a word to figure out here. This word, altogether. Altogether in mathematics is very similar to the sum. In fact, it is the sum. Altogether for us means plus. So here we're looking at the number of single rooms and the number of double rooms together. So that translates for us to being, you've got it, X plus Y. But it said to us it was a minimum of 7. At least 7, and it was a maximum of 12. So the inequality had to face the 12 and face away from the 7. How else could I write that? I can write it as one step, but I'm not going to do that because it's actually going to help us to have it separately to draw it on the graph. Then it says the number of double rooms was to be at least twice the number of single rooms. This is one that we can read from left to right. The number of double rooms, that was Y, wasn't it? At least means that it's got to be the smallest thing. And twice the number of single rooms is 2x. So if I put that together, what I end up with is the number of double rooms must be at least twice the number of single rooms. So I end up with an inequality. That looks y is greater than or equal to 2x. That's the constraints, but there's one more constraint that we haven't taken into account, and it's actually not an inequality. It's actually our optimal function. So we can put it down here, or we can put it down later when they ask for it. It's safer to put it here because it is actually something that governs the feasible region. And the rate is 300 Rand for a single room, 500 Rand for a double room. So it is the rate, let's try that again. The rate is 300 Rand for a single room plus 500 Rand for a double room. Okay, those are the constraints that govern my feasible region. Now I have to draw them. I've been lucky enough to be given a grid, but I have not been given the scale. So it's up to me to choose the scale. Here, what we're going to do is we're going to work out what kind of lines we've got. X is greater than or equal to 1. You've got it. It's a vertical line. So we're going to take a vertical line here, and I think what I'm going to do is I'm going to allow each one of these to be 1 unit, which makes it a little bit easier for us to draw. It would be a bit awkward to draw halves. So here we end up with each block counting 1 unit. So x is greater than or equal to 1 means that I'm going to put a straight line at x equals 1. And it's a vertical line. So here we go. Just going to move it quickly exactly onto. Okay, that's fine. X is equal to 1. All right. Now we've got y is bigger than or equal to 1. Again, that's a straight line, but it's a horizontal line. So here, I take my horizontal line and I draw it. Okay, x plus y is greater than or equal to 7. So let's look at our x-intercept. Our x-intercept, let's cover up the y, and I get x equals 7. Why did I cover up y? Well, y is equal to 0 at the x-intercept. So I'm going to plot 7, 0. Similarly, for the y-intercept, I'm going to cover up the x, and I get y equals 7. And at that point, I join the two dots. If I join the two dots, I end up with a straight line that looks like that. Repeat the process for x plus y is less than or equal to 12, and I end up with a y-intercept of 12 and an x-intercept of 12. Now I've got one more line to draw. That is y is equal to 2x. Remember, this is one of those that is not going to have an x-intercept and a y-intercept that I can join together. Why not? Because it's the origin. So I need to choose an x value to get me another point. Well, choose any x value. Let's choose 2. X equals 2 substituted here will give me 2 times 2, which is 4. So I'm going to plot the point 2, 4. That means I join the origin and the point 2, 4 to get the last line. And if I do that, I end up with a straight line that has a positive gradient, and there we go. Okay, but I haven't done the feasible region. The feasible region is the overlap of the inequalities. So I need to go and work it out. Well, x is greater than or equal to 1. Remember, X I shade to the right or left of the line, not above or below because it's X. It's to the right or the left. X is greater than means I shade to the right. So here I'm going to shade this way. All right? Y is greater than or equal to 1 means that I need to shade here. If I take X plus Y is greater than or equal to 7, the inequality is facing the Y, so that means I shade above the line. So here is X plus Y is equal to 7 line. I'm going to shade above it. X plus Y is less than or equal to 12. Well, the inequality is facing away from the Y, so I shade below. And Y is bigger than or equal to 2X. Well, the inequality faces the Y, so it must shade above. So what happens is I end up with my feasible region looking like this. There's one inequality, or there's one constraint, should I say, that we didn't take into account. And it's one that's implied. It's called the implicit constraint. This is one that it has to be there to make the problem complete, and it's one that we often forget. There's one question you need to ask yourself. Can I have half a? So in other words, can I have half a room? Don't know about you, but I don't know which half you would like. Preferably the one with the bathroom and a little bit of the bed. But half a room, not really going to work. So what needs to happen is we should only really have whole rooms. So the implicit constraint here is that X and Y must be part of the natural numbers, which means in my feasible region, I am only supposed to take into account the whole numbered points. It does become a problem to draw all of these dots, especially if the feasible region is bigger than this. That's why if you have got X, Y is an element of the natural numbers, you have said to the examiner, you understand that I can only have whole numbers. What's the other implicit constraint if you can have half a? So let's say we're talking about liters of oil. If you can have half a liter of oil, of course you can have half a liter of oil. The other constraint for your information is that X and Y must be bigger than or equal to 0. So an implicit constraint, X, Y is an element of the natural numbers. That's if I can't have half a. If I can have half a, the implicit constraint is X, Y is bigger than or equal to 0. In this problem, it must be part of the natural numbers. Okay, so we have now completed the task of drawing our feasible region. Let's go look at what question 2 asks us to do. Question 2 says, according to these constraints, could this hotel have 7 double and 4 single rooms? Then it asks us why. Okay, the double, does that relate to the X variable or the Y variable? Well, we let it equal the Y variable. So here, we're looking at Y equals 7. The single is X, so we're looking at X equals 4. That creates a point for us. The point is, you've got it, 4, 7. Is that point in my feasible region? Let's go look. Here's X equals 4. Where's Y equals 2? 7. There it is, over there. So is it possible for a hotel that's supposed to have these constraints to have 4 single rooms and 7 double rooms? No, because the point lies outside the feasible region. The point lies outside the feasible region. So here, the point 47 lies outside the feasible region. Therefore, we cannot have 7 double and 4 single bedrooms. Well, thank you, grade 11s. We've come to the end of the session. Good luck for your exams, and we'll see you next session.